In this video, we'll be discussing confirmatory factor analysis, which is in some ways an extension of what we've covered previously in this class with exploratory factor analysis. In this lecture, we'll talk through a review of some previous concepts that we've covered, the context of the problem that we'll work through, diagrams for how to express confirmatory factor analysis models, which will take the place of equations that may have been used in things like multiple regression, concerns regarding identifiability, concerns regarding model item fit, opportunities and strategies for model improvement, an example of the process in practice, and finally, an example in software. So we'll start out by reviewing regression. So regression, as has been seen several times in this class, forms the foundation of many other statistical methods that we do. The regression model that we classically look at is y equals the intercept plus the slope, x1, and so on and so forth for as many variables as we have, where y is the outcome variable, beta 0 represents the intercept, beta 1 represents the slope, and epsilon is the error term for the ith participant. One thing that we'll explore more in this class is the concept that epsilon, the error, is simply the variance in y, the outcome, that is not explained by all of the independent variables. That is, it's the reasons why someone may have scored differently on y than anything that we currently are using to explain it. So it's everything else crammed into a single term. This may or may not be reviewed depending on what you've talked about in previous classes, but within the regression context, we have standardized regression coefficients. It's important to realize that variable scale doesn't impact statistical significance, but it does impact interpretation. So if I were including an independent variable of miles versus including an independent variable of inches, assuming these are talking about the same measurements, I'm just changing the scale doesn't impact the conclusion of statistical significance of this term, distance. Our statistical significance tests are elegant enough that they would declare both of these significant or insignificant based on other factors. However, it does impact how we interpret those coefficients. The problem is that I really can't compare the coefficients for miles and inches. And so to allow comparable interpretation, we have to change the scale. One of the ways that we can do this is standardize the independent variable and dependent variable before running the regression. And when I say standardize, there's a standardization calculation where I subtract the mean and divide by the standard deviation. And that puts all of the variables on the same scale. That is, all the variables will now have a mean of 0 and a standard deviation of 1, though each will have their own movement pattern. For each, the new scale becomes standard deviations, and thus that can allow more comparable interpretation because now all the variables are on the same scale. I do want to be careful here. Depending on who you ask in the field, comparable interpretation, comparables taken with a bit of a grain of salt. Some people think that this allows for direct comparable interpretation with no questions asked and nothing more to discuss about it. But others believe, and this is my personal perspective, that when you're comparing apples and oranges, it's important to acknowledge you're comparing apples and oranges, even though you try to put them on the same scale. That is, maybe there are other differences involved instead of just the scale that could have an impact on the interpretation. And so while this does allow more comparable interpretation and is a strategy to compare interpretation and is something that you can do and I personally have done, it's also something that I approach cautiously and with being fully cognizant of potential issues that come into play with these interpretations. Again, because these are potentially different variables that we compare the magnitude of the coefficients. So the coefficients from this process, where I've standardized the independent variable and dependent variable and then rerun the regression, are sometimes called standardized regression coefficients, or beta coefficients, or beta weights. This is a bit confusing because the coefficients in a regular regression model are expressed as betas, but beta coefficients are standardized coefficients. And I've introduced it and it's worth talking about, but it's confusing. The betas in a regular regression model are not referring to beta coefficients. They're referring to something else. So we use the term twice. One, in terms of the betas in a regular regression model, refers to the population level of the relationship. In beta coefficients, this specifically refers to the standardized coefficients, having standardized the independent variables and dependent variables. So they are talking about two different things. It's two usages of the same term. The way that we know one usage versus another usage, frankly, we don't unless it's specified. So the way that we know is that it's specified within the context, which one we're doing. Typically assume regular regression unless beta coefficients or standardized regression coefficients are mentioned explicitly. The new interpretation of these coefficients is as the independent variable increases by 1 unit, the unit now being a standard deviation, the dependent variable increases or decreases by the beta units. And again, dependent variables now also in standard deviations. So as IV increases by 1 standard deviation, dV increases by beta standard deviations. This is true with all the regular caveats. So if we have multiple independent variables in there, it's after accounting for all of the other variables. With a single independent variable, the range for these is between -1 and +1. And with a single independent variable, these are the correlations between the independent variable and the dependent variable. In a multiple regression, it's not always that simple, but with completely independent, i.e. orthogonal independent variables, this should still be true. All right. Reviewing exploratory factor analysis. So recall that exploratory factor analysis seeks groupings, which we called factors, we'll call constructs sometimes, or latent variables, we'll call them a lot of things, among multiple variables/items. And we contrasted this with the cluster analysis, which looks at groupings among individuals, participants. Factor analysis looks for groupings among variables or items. In this, we had different methods we could use to determine the number of factors in the model. So we had a scree plot, we had parallel analysis, we had the Kaiser criterion. We said that one was pretty bad. That was the lambda of 1, or the eigenvalue of 1, excuse me. And we calculated factor loadings for each item and looked at the loadings, but i.e. relationships between the items and the factors. We said that these are correlations if I'm doing an orthogonal rotation, and these are not necessarily correlations if I do an oblique rotation. But every item had a relationship with every factor. And what we tried to do was figure out how many factors we have, look at the relationships between the items and the factors, and then interpret the factors by looking for items that load highly on the factor to determine what that factor is. We could do these rotations I was describing previously to help interpret the factor structure. And one other thing that we did was hide low loading items so that they're not visually distracting. We can kind of see what are the items that are loading the highest on these particular factors and really try to come up with a definition of what this factor is based on what loads highest in it. For each of these factors, we could create factor scores, which is essentially a weighted average or a version of a weighted average of all of the scores on all of the items for that factor using a version of the factor loadings to weight that average. And the interesting thing about these aggregate scores is even if an item didn't load highly, if it had a very low relationship on the factor, it's still used in the aggregate factor score for exploratory factor analysis because the exploratory factor analysis takes into account all those relationships. So the fact that we hid them in the graph when we're trying to interpret the factors or hid them in the table doesn't mean that we actually made them disappear. It's just that we're visually hiding them so that we can try to figure out a little bit easier what the factors are. But if we made aggregate factor scores or actually used this in any meaningful way, these are still there. So even those low loadings are accounted for when we create the aggregate factor scores for exploratory factor analysis. So less discussed in our exploration of exploratory factor analysis, sometimes you'll see factors called latent variables or constructs or unobserved variables or unmeasured variables. So all of these things I will tend to use synonymously in this series of lectures in confirmatory factor analysis and structural equation modeling. So just be aware that when I say factor or construct or latent variable, these are things that go together and are talking about the same thing. So variance and covariance are really at the heart of all of the statistics that we tend to calculate. Really, all of our statistics are analyses of variance, and we have a statistic that is called an analysis of variance, but a regression is in some way an analysis of variance. Not ANOVA. Regression isn't necessarily the same as ANOVA. ANOVA is the same as regression. But anyway, all of these statistical methods are analyzing variance in different ways. And so within this, variance and covariance are actually very, very important concepts, even though sometimes they take a backseat in applied statistics courses. The variance formula may or may not be familiar. Hopefully you've seen it before. And it's really just a measure of movement from the center or mean. So in this formula, I have my score for each individual, that's x sub I, and I'm subtracting the group mean score from it. So that's the distance between every individual and the average. So that's how far away everybody is from the average. That's some measure of variation. I'm raising this to the second power. One of the things that does is get rid of the negative sign. Of course, you can use absolute value for that. And there's a whole branch of statistics that does that. But I'm raising it to the second power and then dividing it by n minus 1, which says I'm adding up a whole bunch of these, but I want to find what is this score on kind of the level of an individual. That's what the dividing by n minus 1 does. And this is my variance term. Covariance is one you may not have seen before, depending on your background, but looks very similar, except instead of x1 minus x bar being multiplied together twice, now we have two different variables. We have my x1 minus x bar, but now instead of being multiplied by itself, that's what that squared is, now it's multiplied by y sub I minus y bar. So this is the movement in x times the movement in y, and this is a measure of how much the movement in one variable is related to the movement in the other. That is how these variables covary. While this formula might not look particularly familiar to you, you're probably familiar with the standardized version of this, which is called a correlation. One of the reasons in statistics, well, depending on the method, we can use covariance and correlation, not quite interchangeably, but we can use covariance and correlation as two options for calculating things. One of the reasons we prefer covariance is because from covariance, we can calculate a correlation, but from correlation, we can't necessarily calculate covariance. That is, covariance has more information than the correlation matrix does, even if covariance is in and of itself less interpretable for the end user than correlation. So if I'm providing this for interpretability as is, I might provide a correlation. If I'm providing this to a statistics program to use in other calculations, I might prefer covariance because, again, it contains more information. All right, well, we've talked about a lot of analyses in this class. So what is special about this one? That is, what can't be done? Can't we do everything with what we've already talked about? Well, consider in exploratory factor analysis, we had all the items loading on all the factors, and we tried to figure out what were the loadings. We tried to figure out how many factors there were, etc. But what if we came in? That is, I went and I found a couple of scales, and I said, well, I already know these items go to that factor, and these items go to that factor, and I know there's two factors. What if, that is to say, we already know which factors items should load in? That's already known, and we'll call that pre-hypothesized or assumed. We assume we know which factors which items load in. Now, breaking this down a little bit more, and again, in terms of our CFA, in CFA, we tried to determine how many factors we should have. In this hypothetical case, we already know how many factors we have. If I know which factor the item should load on, then I know how many factors there are. And again, I also know where the items are loading. So this is all of our all of our exploratory factor analysis that we're walking in assuming. And that's kind of an interesting thought, and frankly may happen more often than not. Sometimes you don't just make up a bunch of items. Sometimes you use items that other people have made. In fact, that's always a good thing to do if you can. So what then would we analyze if I don't have to figure out how many factors there are, and if I don't have to figure out where the items are loading? Am I just done? Do I get to ignore it? Well, no, this is the problem that we're going to investigate with confirmatory factor analysis, because the questions change. We're no longer exploring our data. Now we're trying to confirm the pre-hypothesized structure that we have. That is the number of factors where the items are loading. Is that right? Yes or no? And so to answer this, we're going to calculate statistics, not that explore a number of factors and where items should go, but we're going to calculate statistics that say, okay, you told me this is where items go. How well does the data match with what you're saying? That is, you said item 1 goes on factor 1, item 2 goes on factor 2. How well did the data support that claim? Now, we can do this at a bunch of different levels. We can do this at the item level, that is, are items loading where we think they should be? We can do this at factor level, and this is maybe less in confirmatory factor analysis and more in structural equation modeling when we get there. And we can do this at the model level. That is, overall, does the model seem to be matching with what the data are saying? Do the data align well with the model? So we're going to be looking at this alignment. And again, this is a shift from EFA. We're not looking at number of factors. We're not looking at where items loading. Those are EFA questions. Now we're assuming we know that, and we're testing, are we right? Does that make sense? Do the data match that claim? Yes or no? Now, one cool thing that happens is that these models are not represented in equations. Instead, we do these graphically, and that's actually how we tend to represent them, is graphically. In the software that we'll demonstrate in this lecture set, or maybe I should say in the Amos software, you can actually draw these out and draw the relationships. And that's what you type into the computer to run the model, is drawn relationships. So we do graphical representations in place of equations. There's no y equals beta 0 that we're going to talk about. Of course, we never really looked at that in terms of EFA either, but it is useful to know that is what we're doing in CFA and SEM typically. I should mention that behind the scenes, there's a lot of math here, so I'm more saying what we're going to do in our class. So there are equations. We're just not going to talk about them, and we'll use the graphics to kind of define the equations that we're going to be using. And to be fair, a lot of other people do that too, and almost ignore the math. The computer can't ignore the math. It's got to do all the equations and stuff, but we can. It's important to remember that even though we're not talking about the equations, these models do still have a lot of statistical assumptions, and we're going to have to deal with that at some point. We won't do it in this lecture, we'll do it in the next lecture, but it's important to have in the back of your mind that just because we're doing graphics as the representation of our model instead of equations as the representation of our model, that doesn't change the background statistics that are happening, nor does it change the assumptions that we make. Okay, so how do we graph stuff? Well, we're going to have a couple of different graphical components that each have technical meanings. So just like a little 2 up to the right and above a variable means squared, and has a pretty technical meaning. You can't just write a 2 like that for funsies. If we're going to use graphs as our model, then we have to have very, very specific graphical components. So the first of these is a square versus a circle. A square is going to represent an observed variable, that is maybe one of our items or variables, while a circle is going to represent the latent variable. And recall factors from our factor analysis, those underlying factors are also called latent variables, and we'll do so throughout this lecture as one of the things that we call them. So squares are observed variables versus circles, which are latent variables not directly observed. We'll also have directional arrows, which represent hypothesized relationships between variables. Think about if I believe that IQ has an impact on one's salary. Well, in this particular case, I might draw a directional arrow from IQ pointing to salary, indicating IQ impacts salary. In essence, the left side of our arrow, or the side without the arrow, is going to be the quote unquote independent variable, and the side that the arrow is pointing to is going to be the quote unquote dependent variable. But we'll talk more about this later. So in any case, these directional arrows specify the direction of the relationship. Now, sometimes we'll have relationships with two arrows, bidirectional arrows. If both arrows are pointing to the same variable, that indicates a variance term or an error or a disturbance, which are kind of the same thing. We'll talk about that later. Error is observed, disturbance is unobserved. But in this case, with both, if a bidirectional arrow, just think of it like a big loop almost, where it kind of goes out and comes back in and points to the same variable, that can indicate a variance or error. And if in a bidirectional arrow, that's arrows on both sides, we're pointing to two different variables, that's a correlation or covariance. That is, we're allowing those two variables to relate, but we're not specifying the direction of the relationship. Now, we're taking a little bit of time on the graphical components, and we're talking about some things that we're not actually going to use for CFA, but the reason we're taking a little bit more time with this is because these graphical components are more broad than just confirmatory factor analysis. We're going to be using these graphical components throughout structural modeling, including confirmatory factor analysis, but also expanding into SEM. So here we have an example of a potential diagram. You'll notice the circle or oval on the left representing our latent factor variable. And you'll notice three items, I1, I2, I3, listed in the squares on the right, indicating that these are observed variables. We also have arrows indicating the hypothesized causal flow direction. So that is, I'm assuming the factor is impacting the item. And this is kind of an interesting thing. Normally, or certainly when I first learned about structural modeling, I kind of thought the arrows would go in the opposite direction. That, well, I've got a factor, it's made up of the items. But how we tend to think about this in structural modeling and confirmatory factor analysis is that the items are indicators or expressions of the underlying variable. So I might respond in one way based on my underlying variable to the item. So it's the underlying variable, my underlying intelligence, that influences how I respond to question 1, 2, and 3. So in that case, it'd be intelligence that's pointing to my responses of item 1, 2, and 3 versus my responses of item 1, 2, and 3 pointing back to the intelligence saying this is how intelligence is defined. So what we're saying here is that we believe these items are reflections of my underlying factor, but don't necessarily define it. So they're just, again, reflections of this underlying factor. Now, it's important to realize it's kind of a nuts and bolts thing. You can orient these horizontally or vertically because the arrows define the direction. So I could have the items on bottom and the factor on top, or the items on the left and the factor on the right, or the items on top and the factor on the bottom, depending on what I'm doing. And you'll see these constructed all throughout in those ways. So that happens all the time. Now, one thing involved with these is that sometimes we have some hidden components. That is, components that aren't always shown. And I mention this especially for when you're reading research on this, because they'll show the models, but sometimes they won't show things and you'll wonder if that's there. And sometimes this is true in software too. So I just want to call this out. Anything with an arrow pointing to it has an error. This is a good general rule in SEM, and I'm trying to think if it's ever not true, not that I can think of off the top of my head here. The quote unquote error term can be called an error if the thing we're talking about is an observed variable, or a disturbance if it's a latent variable. And again, we'll get more into that later. And we can express it in many ways. Sometimes it's expressed as a circle pointing to the particular thing. Sometimes it's expressed as that bidirectional arrow. It depends. A common way to diagram it in confirmatory factor analysis is to have, at least for the item errors, to have an actual error term pointing to the item. And again, what does this really mean, that the error term is pointing to the item? Well, what this really means is that within the factor, I have, for the item score, the reason I'm responding to the item, well, I've got the factor contribution as to why I'm responding to the item, but I also have the error contribution. And based on our previous discussion, errors are really everything else in the model. So my factor contribution, it's all the reasons I respond to the item related to maybe my IQ. Error might be related to, hey, my cell phone went off when I was responding to the item. The guy was mowing the grass outside. The item was written in Spanish and I only read English. So there might be a whole bunch of other reasons other than my IQ as to why I answered how I answered on a particular item. And so these things are all captured within that error term. So again, for any given item, I have the factor that I'm looking at, which contributes to my item response, but then I also have everything else in the world that contributes to my item response. And I'm hoping that the factor is contributing a lot to that, because hopefully that tells me a little bit about the factor too. All right. So these models, these pictures, really are just studies of variances and covariances, and all of the analysis that we're about to do purely relates to variances and covariances. These tend to be represented in matrix form. So if you think about having 10 items and doing a study with that, I might have all 10 items listed in the column names and all 10 items listed in row names, and then every entry in the cell is either the variance, where the item meets itself, so item 1, where that meets item 1, the column in a row, that would be the variance of item 1, or the covariance, so where item 1 meets item 3, that would be the covariance between item 1 and 3. Now, there are two big variance-covariance matrices used in confirmatory factor analysis. The first one is the sample or observed variance-covariance matrix. This is what the data are. So I just pull all the data, I look up all the variances, all the covariances between all my observed variables, and this is the sample or observed variance-covariance matrix. The second one is going to be our model implied variance covariance matrix. And this is one that's based on data, but enforces the constraints of the model as it's drawn out. So when we draw our model, we're actually drawing, based on which variables we connect and which variables we don't connect, a variance covariance matrix. So the model implied variance covariance matrix is the one where we drew out our diagram and the computer converts that diagram into a variance covariance matrix, forces the data into that, and we see what the numbers are. Ultimately, we're going to compare these two matrices. We're going to see how does the overall, where we just correlated all the items from the data, the sample variance covariance matrix compare to the variance covariance matrix implied by our model. And if after estimating these are close, then our model seems to align well with the data, and that's a good thing. So the previous slide might seem a bit technical with the discussion of variances and covariances and comparisons of an observed matrix and a model implied matrix, but it actually has a very pragmatic and applied point. That is, what are we actually analyzing? What are the data? And this is important because the classic data that we think about in sample size isn't actually what we're analyzing here. Recall, we're comparing a variance-covariance matrix of the observed variables to a model implied variance-covariance matrix of observed variables within the model that we drew. So here, the unique information, kind of the quote unquote sample size, it's not. We still have our old sample size. We still have to collect lots of participants. But the unique information is now based upon the number of variances and covariances of our observed variables. So consider the case where I have a massive classic sample size, 1 million participants, and I'm collecting information on two observed variables. Well, we might think with 1 million participants, I've got an immense amount of sample size. I can study all these crazy questions. But if I only do two observed variables, I'm going to have two variances, the variances for the first variable, the variance for the second variable, and one covariance, the degree to which the first variable and the second variable covary. So I'm going to have three pieces of information that I can compare between my data and my model. That is, I don't really have a lot that I can test based on just three pieces of information. So I need to make sure that I have more data, i.e. variances and covariances, than parameters that I'm trying to estimate in my model. So when I'm thinking about my model, I need to make sure that I have enough data to measure that. And this consideration is a matter of what we call identifiability. Is the model identifiable? So first off, you don't have to count the number of variances and covariances. I mean, you can if you want to, but if you counted, you're going to find that the number of variances and covariances, the number of quote unquote data points, is p times p plus 1 over 2, where p is the number of observed variables. So if I have 3 observed items, I have 3 times 4 over 2, or 6 quote unquote data points. With these, we'll be estimating all of the unfixed variances, all of the errors and disturbances, and all of the paths in the model. So we have a lot that we're going to be estimating based upon these. And incidentally, identifying all of these pieces is one of the reasons why it's important to be aware of hidden paths so that I don't accidentally forget maybe a variance that I'm going to have to estimate, even though it's not explicitly shown on the graphic. In comparing the number of data points to the number of things I'm estimating, three conditions can arise. One is a just identified model where the number of data points and the number of things I'm estimating are exactly the same. And in this case, I can get some numbers in terms of estimates of the relationships between variables, but I can't test them statistically. I need more data if I'm going to test statistically. I can get an under-identified model, which is that I don't have enough data. I have less quote-unquote data points, variances, covariances, than my estimated parameters. So I'm trying to estimate more than I have data to support. And ultimately, what this leads to is an infinite number of solutions. I don't have just one answer, and that can be our problem. The third situation, and this is the best one, is that I have an over-identified model. That is, I have more data points than estimated parameters. And for statistical testing, this is what I require. I require an over-identified model that is having more data than my estimated parameters so that I can run my tests. Now, it's really important to note here that sample size is still an important thing. It just plays a bit of a different role here. With our classic sample size, number of participants, isn't related to how the model is identified, but it does heavily relate to the stability of the estimates. That is, how much do I trust this? SEM and confirmatory factor analysis tend to require pretty high sample sizes. And so we do want to make sure we are collecting enough participants. And the thing that happens if I don't collect enough participants is I just can't trust my results. So we still need a large sample size. Sample size is still very important. It just doesn't play a role in identifiability in quite the same way. It plays much more of a role in terms of the stability of my estimates. One interesting extension from this is that we can, and probably should, estimate identifiability prior to data collection. Because again, it's not related directly to sample size, it's related to the number of observed variables in my model and the number of things that I'm going to be estimating. So ideally, I should be able to draw out, and this is a reasonable expectation, that you can draw out your SEM model before you even collect data. You're probably going to need to, because you're going to have to figure out what variables you're going to have to collect when you sample your participants. And within this, I can look at how many quote unquote data points I'm going to have. I can look at how many things I'm estimating, and I can make sure that the model is identifiable prior to ever collecting data. Now, I should mention that in the examples that we're going to do in this class, we can do those calculations, but for even moderately complex examples, the determination of identifiability is not necessarily straightforward. So there are some tips and tricks on doing this. You can check out the textbook. It's got some good references. You can check out Google. But ultimately, this can get complex quickly. And so I do want to call that out here. While in our case, in our lecture video and maybe some class assignments, will be sufficiently simple where you could do this by hand. All right, well, this has been an introduction to confirmatory factor analysis and talking about some issues with putting up the model and the identifiability of drawing the model. In the next video in this lecture set, we'll be discussing different measures of model fit.